Une moto volante réellement construite, défiant déjà la gravité, ce qui relevait autrefois de la science-fiction a désormais pris son envol. Portée par la détermination de la Chine à transformer l'imagination en ingénierie concrète, cette moto volante n'est pourtant qu'un début. À ses côtés apparaissent des voitures amphibies capables de glisser sur l'eau, des trains aériens survolant les villes et des systèmes de transport entièrement repensés. Installez-vous confortablement et découvrez certaines des technologies les plus stupéfiantes jamais réalisées. Imaginez une moto capable de quitter le sol et de voler. Cette vision est devenue réalité avec la lazarette LMV 4.96, une création du designer français Ludovic Lazarette, rivalisant avec les technologies les plus avancées venues de Chine. Considérée comme la première moto hybride électrique à réaction au monde, elle combine les sensations d'une superbike électrique haut de gamme et la liberté du vol. En mode route, elle offre environ 100 km d'autonomie, mais une fois le mode vol activé, 4 turbines à réaction intégrées aux roues s'orientent vers le sol et génèrent une poussée colossale. Alimentée au kérosène, elle développe près de 1300 chevaux, permettant à la moto de rester en l'air jusqu'à 10 minutes. Avec un prix avoisinant les 500 000 $, la LMV 4.96 incarne une nouvelle ère de mobilité personnelle futuriste.
The Xpeng X3 represents a convergence of automotive engineering, aeronautics, and advanced electric propulsion, translating the long-imagined concept of personal flight into a functional, road-legal vehicle. At its core, the X3 is built around a lightweight yet rigid structural frame designed to support both terrestrial loads and the aerodynamic stresses of vertical flight, which is a significant challenge given its mass of approximately 1.9 tons. The 8 electrically driven rotors are distributed symmetrically to ensure balanced lift and redundancy, allowing the vehicle to maintain stability even if one propulsion unit underperforms. These rotors are governed by a centralized flight control system that continuously analyzes data from gyroscopes, accelerometers, GPS, and LiDAR sensors, making thousands of micro-adjustments per second to maintain attitude and altitude. In driving mode, the flight hardware is either folded or aerodynamically neutralized, enabling the X3 to behave like a conventional electric car, with familiar steering, braking, and acceleration characteristics, which reduces the learning curve for users transitioning from ground travel to air mobility. The shift from driving to flight is designed to be seamless, relying on automated checks of battery charge, rotor status, weather conditions, and surrounding airspace before allowing vertical takeoff, thereby minimizing pilot workload and safety risks. Once airborne, the vehicle's electric propulsion system provides sufficient thrust to reach speeds of up to 130 kilometers per hour, while remaining remarkably quiet compared to traditional helicopters, a key advantage for urban environments. The endurance of up to 35 minutes reflects a careful balance between battery energy density and payload limitations, illustrating current technological boundaries while still enabling practical short-range aerial commuting. The panoramic 270-degree canopy is not merely a luxury feature, but also enhances situational awareness, allowing pilots or autonomous systems to better perceive obstacles, landing zones, and surrounding traffic. The inclusion of both manual and autonomous flight modes highlights Xpeng's vision of scalability, where experienced users can retain direct control, while less trained passengers rely on AI-assisted navigation and collision avoidance. Collectively, these elements position the Xpeng X3 not just as a novelty, but as an early blueprint for a three-dimensional transportation ecosystem in which roads and airspace merge into a unified mobility network. The BYD Yangwang U8 embodies a radical reinterpretation of what a modern luxury SUV can achieve by extending its capabilities beyond solid ground and into extreme environmental conditions. Its most striking feature, the emergency flotation mode, is the result of a comprehensive integration of vehicle sealing technology, electronic control systems, and structural buoyancy management. When onboard sensors detect deep water or sudden flooding, the system automatically activates a sequence that isolates the cabin from water ingress by sealing doors, vents, and critical joints, while simultaneously shutting down the internal combustion engine to prevent mechanical damage and electrical hazards. The vehicle's body design, combined with controlled air volumes and weight distribution, allows it to maintain positive buoyancy, enabling it to float steadily for up to 30 minutes, long enough to escape flood zones or await rescue. This function is not intended to replace a boat, but rather to provide a critical safety margin in unpredictable environments, reflecting an increasing emphasis on resilience in vehicle design. On land, the U-8's adjustable hydraulic suspension plays a central role in its versatility, allowing the ride height to be raised for rough terrain or lowered for stability at higher speeds. This suspension system works in concert with advanced sensors that continuously adapt damping and stiffness in real time, ensuring both comfort and precise control regardless of surface conditions. The ability to rotate 360 degrees on the spot, enabled by independently controlled electric motors at each wheel, demonstrates a sophisticated use of torque vectoring, allowing the vehicle to pivot around its own axis without forward or backward movement. This maneuverability is particularly valuable in tight off-road scenarios where conventional steering would be ineffective. Beyond individual features, the Yangwang U8 illustrates a broader engineering philosophy in which safety systems, electric drivetrain technologies, and intelligent software are tightly interwoven. Rather than treating luxury, power, and innovation as separate goals, the vehicle integrates them into a cohesive platform, showcasing how the Chinese automotive industry is increasingly capable of delivering technologically ambitious vehicles that address real-world challenges while redefining user expectations of what an SUV can be.
The fully autonomous aerial monorail developed in China represents a significant shift in how urban transportation systems are conceived, built, and operated. By elevating the rail infrastructure above ground level, the SkyTrain directly addresses one of the most persistent problems in modern cities, the saturation of road space. Instead of competing with cars, buses, and pedestrians, the system creates a dedicated transit layer in the vertical dimension, allowing cities to move large numbers of people without demolishing existing neighborhoods or expanding road networks. The 10.5-kilometer line demonstrates how elevated rail can be integrated into dense urban environments with a relatively small physical print, supported by slim pillars and prefabricated guideways that minimize disruption during construction. The fact that the entire system was completed in just 7 months highlights the effectiveness of modular construction techniques and standardized components, which significantly reduce both cost and construction time compared to traditional metro systems. The SkyTrain's fully autonomous operation is central to its efficiency and safety. Without onboard drivers, train movement is controlled by an advanced central system that continuously monitors speed, spacing, track conditions, and passenger load. Sensors, cameras, and communication networks allow the train to respond instantly to obstacles, system anomalies, or changes in demand, reducing the risk of human error while maintaining consistent performance. Operating at speeds of up to 60 kilometers per hour, the system is optimized for short to medium urban distances, where frequent stops and reliable timing are more important than extreme speed. With a capacity of up to 200 passengers per train, it can absorb a substantial portion of commuter traffic, easing pressure on congested roads and conventional public transport. From an urban planning perspective, the elevated design also improves land use efficiency.
Ground-level space beneath the tracks can remain available for pedestrians, green areas, parking, or commercial activity, rather than being consumed by wide roads or rail corridors. Noise and vibration are reduced through the use of rubber-tired bogies and lightweight materials, making the system more acceptable in residential areas. Energy efficiency is another key advantage, as the electric propulsion system benefits from regenerative braking and optimized acceleration profiles managed by automation. Collectively, these elements position the autonomous SkyTrain not just as a technological achievement, but as a practical model for future cities seeking scalable, safe, and space-efficient mobility solutions in an era of rapid urbanization. The EHang 216S represents a decisive step toward fully autonomous urban air mobility by rethinking both aircraft design and pilot responsibility. Instead of relying on a single large rotor or a small number of propulsion units, the aircraft uses 16 independently controlled electric rotors distributed symmetrically around the airframe. This distributed propulsion architecture is fundamental to its safety philosophy, as it allows the vehicle to maintain stable flight even if one or several rotors experience reduced performance or complete failure. The onboard flight computer instantly compensates by redistributing thrust among the remaining rotors, preserving balance and control without requiring human intervention. This redundancy is particularly important in dense urban environments where emergency landing options are limited and reliability must be exceptionally high. The fully autonomous nature of the EHang 216S marks a radical departure from conventional aviation, which depends heavily on pilot skill and situational judgment. All phases of flight, from vertical takeoff to route navigation and precision landing, are managed by artificial intelligence systems that process data from GPS, inertial sensors, radar, and communication links with ground control. Before each flight, the system evaluates weather conditions, airspace restrictions, battery status, and passenger load, ensuring that the mission remains within safe operating limits. During flight, real-time monitoring allows continuous adjustment of speed, altitude, and trajectory, while collision avoidance algorithms help prevent conflicts with other aerial vehicles or obstacles. This high level of automation reduces human error, which remains one of the leading causes of aviation incidents, and makes aerial transport accessible to passengers with no piloting experience. Performance characteristics such as a maximum speed of 150 kilometers per hour and an operational altitude of up to 3,000 meters position the EHang 216S as a practical solution for short to medium urban and suburban routes rather than long-distance travel. Its electric propulsion system produces significantly less noise than traditional helicopters, addressing one of the major barriers to public acceptance of low-altitude flight over cities. Energy efficiency and emissions-free operation further align the aircraft with sustainability goals, especially as cities seek to reduce their environmental footprint. The compact cabin, designed for 2 passengers, prioritizes stability and efficiency over luxury, reflecting a vision of aerial taxis as an extension of public transport rather than a niche experience. Taken together, these elements illustrate how the EHang 216S is not merely a futuristic concept, but a carefully engineered response to urban congestion. By shifting a portion of passenger movement into the vertical dimension and removing the need for onboard pilots, it proposes a scalable model in which airspace becomes an organized, automated layer of urban infrastructure. This approach suggests a future where intelligent flying vehicles operate alongside roads and railways, fundamentally transforming how cities manage mobility, time, and space.
D'autres innovations marquent également cette révolution, comme l'agneau ET9, capable de secouer la neige de son toit grâce à une suspension hydraulique intelligente, ou encore la Honda Moto Compacto, un scooter électrique compact, léger et urbain, conçu pour les trajets courts. Le Xiaomi 9Bot Mini, quant à lui, illustre la mobilité intuitive grâce à son système d'auto-équilibrage contrôlé par les mouvements du corps. Des voitures volantes aux trains autonomes, en passant par des véhicules capables de flotter ou de s'équilibrer seuls, le futur du transport n'est plus une promesse lointaine, il est déjà en marche, transformant notre manière de nous déplacer et redéfinissant l'expérience humaine dans un monde toujours plus intelligent, durable et connecté.